Good afternoon, everybody. So in the next half an hour, we'll be having a discussion about how to harness AI for climate. We'll be talking about the possibilities, which I'm pretty sure you're all fairly familiar with, but maybe there's one thing or two we can tell you that's new. But I think really crucially, we'll be talking about the risks. That's actually a key point as well. So how to harness AI in the correct and the best possible manner. And to introduce ourselves, my name is Johannes Schmude. I'm a senior research scientist with IBM just north of New York. We are building large foundation models, large AI models, that basically capture the processes of our natural environment and can thus be used to study climate and sustainability questions.
Hi, I am Noman Bashir. I am Computing and Climate Impact Fellow at MIT Climate and Sustainability Consortium. So MCSC is a consortium which has a set of researchers that work with member companies and also MIT faculty to accelerate decarbonization of various societal sectors. And as a computer scientist, my interests lie in sustainability of computing and what it means for computing to be sustainable, what are the challenges in reducing the environmental footprint of computing. And as a computer scientist, I look at the systems that can be built to have responsible AI or environment-friendly AI. So with that, I have a question for Johannes, that you mentioned the use of AI and building foundation models at IBM. Can you please say a little bit more about that? What kind of work is being done at IBM on these topics?
Yeah, I'd be happy to do so. So I think there's several layers to this question, okay? Let's start with probably what is best known to the audience. When we talk about foundation models or generative AI models, we typically think about language models, okay? So language models, obviously, what we know, we expect huge efficiency gains in this space. We've seen these already realized. We see this, that these models can also unlock knowledge. So when we think about research in various areas, foundation models can read research papers and basically distill the information much more quickly than, non-domain expert researchers can. And then crucially, we see productivity enhancements, okay? This sort of comes to the point if you look at application modernization, where, for example, we, build models that translate, applications from COBOL to less ancient languages. But I think we expect the biggest impacts to maybe be actually outside the range of language models.
Yeah, so exactly. There has been a lot of recent hype around generative AI and language models, but I believe that at IBM, you have been working on non-language models for a wide range of climate-related applications. So can you please tell more about that?
Yeah, thank you so much. And let me say, this is actually work that happens largely in an open science collaboration with colleagues at NASA and Oak Ridge National Lab. So we've been building foundation models, as I said earlier, that capture the physics of the natural environment, okay? Right. So let me say for a second what this means. And to say this, let's take one step back and say how conventionally weather forecasting and, more importantly, climate modeling is done, okay? So when you think about climate and climate projections, this is basically thinking about the dynamics of our natural environment. These are known physical laws. And for decades, the process was, graduate students and interns and researchers write on these equations. This is then coded up and run in supercomputers and massive simulations, okay? So what we see now in the last few years is that we see large AI models that actually replace or emulate these simulations. So the impact of this, I can put this very simple in sociological terms, okay? If you went to a meteorological conference 2-3 years ago and said you want to use AI to forecast the weather or predict the climate, they would have thrown you out because it's anathema. It's basically traditionally physics equations, physics models, you simulate up an issue, okay? Now this has become a discussion topic that actually people accept. And this is sort of, maybe not everybody's aware of this, but there's a mini revolution happening in the space of climate modeling and weather modeling.
So beyond just weather modeling and meteorology, there is a vast amount of data from Earth observations collected from satellites and other sources. So is there a potential for AI to leverage that data that could not be processed using traditional models or would be impossible? Yeah.
Actually, I think before we go to this point, I think there's one elaboration we have to make on the previous point. Because, you might ask yourself, why is this transition happening? I told you there's some transition happening among climate scientists, from non-AI models to AI models. The reason why this is happening is when you transition from a supercomputer to an AI model, it goes from weeks to minutes. Okay, something that takes weeks to simulate, you can now simulate in minutes. This is obviously when we as technologists listen up. There's efficiency gains to be made, okay? So when we think if we can model our climate, 1,000 or 10,000 times faster, what does it mean? We can run simulations at much higher spatial resolution. That means we can think about impacts of climate, at much higher spatial resolution. So when we think about, adaptation measures, when we say what area is going to be affected by heavy rainfall and floods in 2095, we need higher resolution climate models. Conventional models would take huge compute resources. No? Similarly, when we think about, these efficiency gains, we can also think about more possible scenarios. If I run 10,000 times faster, I can run 10,000 different climate scenarios and still get like 10 times the speed up, okay? So this is really important that the way we think from a mathematical modeling side about climate is actually changing, okay?
Great.
And I think with this, should we return to the satellite data, or?
Yeah, sure, please. Yes.
Okay, so there's a second point to make here, okay? And as I said, this is sort of these applications lie outside the space of traditional sort of, conventional Gen AI. So what we saw in the space of meteorology, is that AI models understand physical processes, okay? And weather and climate is not the only case where we have data. You were saying earlier, we have satellite data. We have satellite instruments, and there's a space where we say, can we train AI models to understand satellite data?
Right. Yeah, so what are the key benefits that are unlocked by AI models in processing satellite data that was not possible before?
Yeah, that's a really excellent point. No? So, because satellite data has been around for decades. It's not a new thing. The key point, first of all, is to say, for those not familiar with this, Earth observation data is huge, okay? So Sentinel-2 satellites by the European Space Agency generate something like 3.2 terabytes a day. This is just two satellites, no? So if you think between the commercial sector, the public sector, all the information we're gaining about our Earth is absolutely vast, okay? And the first question you can ask yourself is, what information can I get out of this data, okay? For example, can I find greenhouse gas emissions, methane emissions, CO2 emissions in satellite images? Yes, I can in principle, okay? Similarly, I can say, can I quantify above ground biomass? It helps me to think about carbon sequestration from satellite images. Okay, but to return to your question, the problem with conventional methods is it's a very laborious process, no? You maybe have some satellite images, but finding signal in the data is very difficult, no? So traditional research is very, very nice that spends lots of time identifying signal from the data, trying to extract the signal to then sort of quantify methane emissions from pipelines, other GHG emissions, or is to find above ground biomass, no? But I think the key point where we see now that has changed when we transition to this AI perspective is we can reduce the time to insight considerably, okay? This is sort of the general promise of data-driven learning, that we say we just learn from data. And to say the final point is, because we move foundation models, we can do this with much less labels, okay? So let's say we wanted to build an AI model to find methane emissions. Traditionally, you might need 10,000, 100,000 labeled methane emissions, which is actually hard to come by. They're not typically being shared. And when we transition to a foundation model, you can do this with maybe 1,000 emissions.
So far you have talked about the potential or the promise of AI. How much do you see this deployed in practice? Are there companies that are actually leveraging some foundation models or some use cases that you have seen in practice?
Yeah, this is a good point. So in companies, we've seen this, okay? So I was mentioning earlier quantizing above ground biomass. This is actually something we're putting into production, again, for questions like, if you think about, carbon markets, you have some piece of land that is some carbon emissions are in there. This is supposedly a financial value. Can you quantify this automatically, you got a piece of paper, some document with a picture of a forest saying, there's some carbon emissions here, there's some carbon credits here. If you want to actually monitor this automatically, this is something we're putting into production, But looking beyond ourselves, we see ECNWF, the European Center for Mid-Range Weather Forecasting, is actually putting a weather forecast model based on AI into production. Now,
so I had a follow-up question based on when you talked about carbon credits. So in carbon credits, and there are a lot of there is a lot of talk about leveraging AI for ESG applications, and I believe you have some interest and expertise in that area. Can you?
Yeah, so actually we have colleagues who build AI models for ESG questions. These are actually language models.
Okay.
Technically not really my expertise. I should refer to my colleagues here. But let me make one comment on the earlier issue. for East and WF, so we don't misunderstand each other, because it's important to think for these applications, there's different thresholds to application, no? For weather forecasting, this is for like, natural disasters, airline safety, etc. When I say this is production, there's running the model every day. Like your weather forecasts still come from conventional models that have been understood for decades, no? So that's really important to point out, to not like misqualify this, but for different applications, the threshold for application can be sort of at a different height, no?
Okay, yeah, makes sense.
Okay, so I think we've spent enough time talking about the applications now. I think one key promise you made to the audience up front is that we talk about the risks, okay?
Yes, sure.
And I think, this is the point where we turn the discussion around a bit, because let me say this, I think one of the things I was really looking forward about this discussion is, that our colleagues at MIT thought really deeply about sort of the wider societal implementations. Now, as you can hear, I'm a very enthusiastic person about building things on these large-scale AI models, but I think it's good to take a step back and think a bit what the risks and the wider implications are, as you have done in your recent white paper. So can you tell us a little bit, what are the potential risks of basically the rise of Gen AI?
Yeah, so I think the current discussion, as you pointed out, have been mainly around the benefits and the promise of AI. But we have not really, so these are all expected benefits, but not realized benefits. In some applications, as you pointed out, that these may be realized, but for others, it's just our expectation. So within that, when we look at the benefits, there are other costs that are being ignored. Like these costs include environmental costs and system level, like socioeconomic costs that are being ignored in this one-sided valuation of generative AI. So if we decompose the costs a little bit, mainly what we have talked about is application-related benefits. So you use Gen AI, you improve some process. But there are compute-related impacts, which come from running data centers that use energy, which emits GHG emissions. They use water. There is a need for material extraction to to develop servers and buildings and whatnot. And then there are system level impacts that may include like supply chain contention. For example, in the COVID, there was a shortage of chips, and it impacted how and who can access the chips and GPUs. And also on the electricity access side, there are implications on if there is a more demand for like generative AI and data centers, do you allocate the available energy capacity in the grid towards building or supporting more data centers, or maybe decarbonizing transportation or buildings and stuff? So in this whole picture, I think the focus is generally on the benefit side, and the social and environmental aspects of AI are often ignored.
That's really interesting. So I think one question is really important to say, because you mentioned very different types of sort of, social, environmental, supply chain aspects. Some of these are very clearly like sort of AI specific, like basically chip shortages, no?
Yes.
But I think in many cases we've seen, so what is different for Gen AI? Because we've seen things we could have said, oh, what are the environmental inputs of the move to cloud computing? Or what are the impacts of, wider adoption of other computing paradigms? So what is so special about the Gen AI transition compared to other transitions historically seen in computing?
So I think there are three things that differ for Gen AI when compared to other computing applications. So first one is the energy-intensive nature of these models. For example, if you do a Google search and it costs you, let's say, 1 unit of energy, doing the same search with ChatGPT or a similar language model would cost you at least 10 times more energy. So these models are require massive energy to train, and it can span multiple days and have like thousands of GPUs. And then even the inference, when you actually make a query and it generates a response, that is very costly, as I mentioned, the 10 times more energy intensiveness. The second angle is about the scale of deployments. If you look at cloud computing, normal people don't have access to cloud computing. No one goes to AWS and spins up a machine and runs some workloads. However, on the generative AI and these models, you see that anyone can go to OpenAI website or any other like website or Bard and just like ask queries. It is also being implemented and integrated into various applications such as Instagram and other applications that people use. So as soon as something is deployed, it is automatically available to millions and billions of people, and that scale is very, very different from other computing applications. And finally, the third thing that is to be considered here is the pace at which things are changing. So the innovation in computing and other fields in the past have been relatively slow when you compare it with the generative AI advances. So with generative AI, every 18 months or like 1 year, we are doubling the size of the model that is being used, and the applications are also increasing. And they have this massive energy demand. If you were to ask me about building sustainable data centers that are required to support the current generative AI demand in the next 50 years, that would be possible and tractable kind of problem. But if you were to do that in the next 3 years, I don't think that is possible. So our ability to build sustainable data centers cannot keep up pace with the current growth rate in generative AI. So I think these are three kind of fundamental elements that make this generative AI growth different from any other computing and like broader societal innovations, and that is why there are more risks involved in this generative AI growth.
So let's go into some detail on some issues here, okay? Because I think there's some really interesting points. The last one you said was basically about the increase of size in AI models, okay? And obviously, from our perspective, we sit in meetings saying, to one extent, how can we make the models bigger?
Yeah, right.
And then we also say, actually, at a certain scale, they become impractical. There's lots of research efforts in pruning model and making them efficient, But admittedly, this is primarily driven by deployment concerns. Can you run something on a smaller device at the edge, etc. But what I'm curious about is, so you said we see a doubling in model size. Do we also see like a parallel doubling in resource consumptions? Because there is some efforts on efficiencies there. No? Is that entirely clear at this stage?
Yes, I think there is significant effort in reducing the energy footprint of models, but the rate at which we are growing the size and also the number of models trained as well as the inference, the energy optimization and energy efficiency gains cannot keep up with the rapid innovations in the size and the energy demand. So definitely it controls it and tames the energy demand and carbon footprint and broader environmental impact of Gen AI model to some extent, but it does not fully overcome it. Like the innovations in energy efficiency are not able to keep up with the innovations in the model size and the capabilities and resource requirement of those models.
Okay, and then thank you. So let's return to the second point you made. No, I think the second point you were saying was, and let me paraphrase, and I'm going to go on a limb here, okay? But I think you were saying that this is largely driven also then by the basically ease of use to the general public. No, that basically is not like a technology that is used, by a few high-performance data centers, by some sort of expert researchers or something like this, like traditional high-performance computing is. You're basically saying that this all lands in consumer products. Consumers are expected, or ideally, for efficiencies, like use these products all the time, and that drives sort of this massive consumption. Is that correct?
Yes.
So, does it mean that when we compare to other industries where consumers make, carbon resource intensive decisions. You buy airline tickets, you buy things through supply chains. Is there similar things about incentives for consumers in some sense? Like the same way I might offset my carbon emissions when I buy a flight ticket, whether people do or not, Is there similar questions in this space here?
I think incentives are one of the major problems in this space in my mind, because consumers, like if I look at myself, I get most of the computing applications for free. My Gmail is like free. I can search for free. Even ChatGPT basic version is for free. So I don't really have an incentive to be judicious about my use of computing power. Even if some application does not give me huge benefit because I don't see or bear the cost directly. There is no monetary cost for me to like use ChatGPT. I don't have any incentive to go for or be judicious. Like like if Google search does something for me and it gives me the right answer, people may still be attracted towards using ChatGPT or like using some other resource-intensive technology. So I think the main problem with this is like I think for companies it's a different equation because they may be paying for the cost of training and cost of inference, and they will have to be a little bit cautious. But for normal users, they don't really have an incentive to be climate friendly. And it's not that they don't want to be. In a lot of cases, the problem is that they don't have any visibility into it.
Yep. And I think that's actually like a key point. So I think obviously we want to sort of, talk about possible solutions. No, we talked about the promise, we talked about the risk, but I think before we doing so, for the wider discussion, obviously from the analysis that you did with your colleagues at MIT, MCSC, we can say sort of, do the benefits outweigh the costs? Is that like a clear picture that you guys have already?
I think based on the applications that you pointed out and the productivity and efficiency gains we can achieve, especially for sustainability related applications. So definitely there is like numerous benefits, and as you pointed out that there are actual applications where you can see the realized benefits. However, I don't think that is going to be the case for all the applications. And in some cases, it can be actually counterproductive. For example, you can use generative AI to make fossil fuel powered plants more efficient, and that will make them more competitive with other greener technologies, and that means they can they can be in the market for longer. Also, one other thing that I was reading an article yesterday that said basically because we don't have enough generation capacity to support data centers, some places are actually delaying the retirement of fossil-powered plants to support this additional energy consumption due to generative AI. So either directly or indirectly, it can actually have negative environmental implications.
So maybe also one question to ask at this stage is, so typically when we see technology, there's always these hype cycles, no?
Right.
So obviously we know, what we see now basically for Gen AI, there's been like a massive hype over the last 12, 18 months. I think we already see like some consolidation in, certain industries. You see like for certain startups, things don't quite make sense. I think it's an interesting question. Do you have any reason, expectations, if a consolidation in the economic sphere goes to a consolidation in resources? Or do you think, the resource consumption is going to keep growing, even though the number of companies sort of using Gen AI might actually sort of flatten out?
I think the resource consumption will keep going up because of multiple things. First one is that there are a lot of applications that are yet to be tapped by like generative AI. So first that, and second, the access to generative AI or even internet is limited to, is not available to all of the people in the world. So as we have more and more people accessing the internet and these generative AI tools, the demand is going to go up, even if it is served by a handful of companies.
Yeah. Okay, so what's the solution? What are we going to do? And we're going to open the floor to Q&A, so maybe one of you guys already knows. But let's keep this a bit of some tension here before someone gives us the solution. So what do we think is the solution?
Yeah, so I think in our white paper, what we said was that before we actually do any kind of regulation or anything else, we need to actually incorporate the cost into this benefit equation. So everyone talks about benefit and we can quantify that for some applications, but we need to have a comparative evaluation framework where for some application of generative AI, we will be able to say that this provides this much benefits, but it comes at this much environmental cost. And then maybe if you have a limited generative AI capability, you will direct your capabilities toward an application where you get most bang for the buck.
But then I think the question to sort of say, from my point of view is, please.
Yes.
I've got one. I don't think it's I was interested when you said that a AI query will eat up 10 times the amount of energy as a regular search query. Are you saying that in that instant, in doing the search, that causes that much carbon to be used? Or is it that you're looking at the overall carbon cost of creating the LLM and then dividing by the number of searches?
This is just for the inference, and training costs are separate. Yes.
I think in general, inference costs, I mean, even though training costs are immense, I think when we really took at sort of consumer applications, inference costs are actually large, no? The driving factor, no?
Yeah, over the life cycle of, because inferences are, like many more inferences are done, individual inference don't cost a lot, but it is still higher than Google search.
That's something that really surprised me when I learned about this. Sort of, I think from, the training cost often is so massive now, these headline numbers, use like 1,000 GPUs for like a month, You really think this is like the driving thing. And I always thought like inference is like cheap because it's nothing, no? But then you learn when you do inference at scale, it actually becomes absolutely massive. And this is why we say driven by the utility, no? Yeah. Okay, so let me sort of say one question, because we said about, you're saying about making people aware of sort of the risks or the impacts, no? Obviously, as a technologist, I have to say, like, is there a risk this stimmy innovation, no? And I'm not just saying this for like self-serving greediness that I want to keep, using technology and innovating, but also because we said there is benefits for climate, no? So is there like a clear idea, or is it the typical thing, trade-offs, my own sort of, want to use something versus trying to take a step back for the greater good?
I think there will always be a tension between the two sides. Like, you want to be innovating, but at the same time, you don't want the innovation to go at a pace that we reach a dead end point where we cannot track back. So climate-related impacts are becoming huge, and we may, if we keep going without any kind of oversight or at least analysis of what are the climate implications, we may reach a point where we cannot just stop and say that, oh, this has now we are at a point where we can return and stop growth because the climate implications are huge. So I think both of these things will go hand in hand, that you keep innovating, but also you are at least before governing, you are at least aware of that this is what the impact is. And then maybe markets or people's own behaviors can change how technology is used.
Okay. I think we want to talk about the challenges, but I think at this stage, also looking at the time, let's pause. Should we pause for Q&A?
Yeah, sure.
I think that's the question. So let's pause for a second. Is there any further questions, comments from the audience?
Hi. I want to open up a question about water usage in data centers. Many people don't know data center uses your utility water, just tap water. Think of a steel plant using your water. And the problem with that is generative AI it needs this hyperscale data centers, which consumes a lot more water than regular data centers. But for a data center, it's cheap to make a deal with the utility company because they can consume a lot more water. But what happens is it has a social impact. The public don't have water, and their cost goes up. So now they are going and setting up the data centers in developing and emerging countries who doesn't know about these things. It's triggering a bigger issue than what it actually is, and it's a very serious issue. So what are your thoughts on it?
I think, sorry if I may say, I think these are exactly sort of the questions that your white paper highlights. So thanks for actually reflecting on this. And I think maybe one way, I see you have more questions. So you want to give a brief answer? Because I think how we resolve these challenges, basically your question is how we resolve these challenges together, no? So let's give a brief answer.
So I think a very brief answer to that would be, first, we need to be able to measure, because the water impact of data centers is not as visible as carbon footprint impact, which has been studied widely. So the goal should be to enhance the visibility into water consumption, and then basically look at how it impacts local communities, because it has more local impacts rather than global impact as the carbon footprint has. I'm sorry, I wanted to just go to the second question.
Let's continue over there, please.
So something similar. I want to hear more on the solution part, because you're right. So we're going to see load growth 15%. We haven't seen load growth in 10 years, and that's only going to happen because of data centers. So there's a huge climate implication, and utilities are already putting more gas, not shutting down coal plants. It's not a small problem, it's a very big problem. But Google and Microsoft just signed projects with SMRs. They're trying to get battery storage on the grid. Do you think that should be actually the way to do it? That should be the only way to do it? Because if we not do regulations, it's not going to happen. And I live in North Carolina, it's not happening. So.
I think you're touching already the answer, and that's actually what sort of came very clear in our discussion. And this is almost going to be like a bit, it's going to be like a cop-out answer. It's very clear this is a multi-stakeholder problem. Yes. I think that's the immediate question, no? So as you cannot, as a tech company, unilaterally say, we stop using data centers, and then we don't have any business, because duh, you know? At the same time, we also set incentive structures for consumers. We can say, please consumers, please just solve this for us and be very mindful with your queries. Good luck with that, no? Because even then you have competitiveness problems. So I think this is a typical problem. And that's why I said similar about transport, logistics, airlines, one of these decarbonization problems with multi-stakeholders. No, I think also that's what you found in your report, no?
Yeah, I think tech companies' involvement in this space has been helpful because they incentivize the deployment of renewable energy, and so all of that is good. But also, I think we need to understand how they have early movers advantage, and as you integrate more and more renewable energy into the grid, it becomes more challenging task. So there needs to be a balance between how much credit they receive, because based on these contracts, they have this, they are able to claim that they are operating on zero carbon energy and whatnot, which is true based on the market-based mechanisms, but may not be true for the grid-wise. So I think the solution is that tech companies and their financial might would be helpful in bringing new technologies, new green technologies such as storage and other things into the grid. But at the same time, we need to balance it with right amount of regulations that make sure that there is a long-term solution, not just the short-term solution, and the solution is not only for the tech companies.
So I think we have, towards the end, but I think we have a last question. We can turn this quickly because it's really the last one. Hope that won't kick us off the stage. So please.
Sure, yeah, thank you for the discussion. You mentioned that AI can be used to improve the efficiency of fossil fuel power plants. And so I was curious if, how do you believe it's prudent to increase the efficiency of those power plants rather than displacing and decommissioning them altogether?
Sorry, can you repeat the question? So I understand. Yes, please.
Sure, yeah, no, I mean, is it, from an emissions reduction standpoint, prudent to improve the efficiency of the fossil fuel power plants rather than decommissioning them altogether?
Yeah, so I think there has been some work on that quantifies the improving the efficiency means that you reduce the cost of operating those, not necessarily that you don't really reduce the emissions from generating 1 unit of energy from those plants. If that was the case, that would be a net positive maybe, but at least from the operating cost standpoint, I think generative AI is used to remove inefficiencies in their operation, and that leads to them being more cost competitive, and that leads to delayed retirement.
So with this, thanks to audience for these questions, for the Q&A. Let me also thanks to you. I think I really enjoyed preparing for this. So thank you very much, and have a good conference.